Good afternoon, everyone. Did you guys, I guess tomorrow you're attending, some of you, the next laboratory, right? That's going to be the last laboratory that we do downstairs. And we'll see if we have time to do another laboratory in the computer lab using a reservoir simulator coupled with geomechanics. I think we'll have time for that, but I'll confirm that later on. From those of you that did the test, were you able to get breakouts or not? Yes? Like, did the entire sample break? Or, yeah, I think that because this time we made the holes too big, and that's why they completely broke. But if you were lucky, or if you're lucky tomorrow, you might be able to get just breakouts without the sample failing completely. But I think most of you could observe the tensile fractures, right? All right, let me tell you that when you put your lab together, and probably as Zihao explained before, the theory is not going to match exactly what you see in the experiment, and that's because the sample that we use, it's fairly small compared to what the theory assumes. The theory assumes an infinite medium, and in the laboratory we have a very small sample and a large wellbore, so the equations may not exactly work as you expect, but you have to compare that anyways. And the report is going to be due next week. Okay, but wait, next week is exam, right? So it's going to be due then the week after the exam. I'll talk to Zihao about that. All right. So the last thing we talk about, let me bring my notes here, which are a little bit more organized than what I wrote, was how to define the mud window based on failure around the wellbore, either by shear when your pressure or your mud weight is too low, or by a tensile fracture whenever the mud weight and the mud pressure are too high. And the last thing that we discussed was what would be the absolute maximum upper bound or the safest upper bound whenever you have a situation in which your calculated breakdown pressure is either smaller or larger than the minimum principal stress. And I said this already last class, but I said that very quickly, and it's very important. So I'd like to just complete this, and then we'll move on. Okay. Whenever you calculate a value of breakdown pressure, which is higher than the minimum principal stress, and let me move this down because we'll need this space. I'm just moving this thing down over here. And I have my eraser today, so I can erase this. Okay. So whenever you calculate PV larger than S3, and eventually your pressure in the wellbore gets larger than PV, the result of that is that because PW, pressure in the wellbore, is larger than PV, and PV was already larger than the minimum principal stress, this is going to lead, if this is a wellbore, to a small hydraulic fracture that then, as long as the pressure in the wellbore is larger than the fracturing pressure, is going to propagate into a large hydraulic fracture. We're going to see later on what is the actual pressure that you need in order to propagate that fracture. But if the pressure in the wellbore is larger than the minimum principal stress, already there is a chance that this fracture may propagate, and might propagate quite far away. When you have a large hydraulic fracture during drilling, you are losing a lot of drilling mud, and that what causes lost circulation because you're not recovering the same amount of mud that you're sending into the wellbore. Sometimes this may not be too bad, but some other times it is, especially, for example, in offshore locations where the amount of drilling mud that you have is limited and it's quite expensive too. So you don't want to do this. That's the first case. However, there is a second case in which your calculated breakdown pressure is going to be smaller than the minimum principal stress. And if you get the wellbore pressure to be higher than the breakdown pressure, you should have a small tensile fracture as long as that wellbore pressure is also smaller than the minimum principal stress. Again, if you go over the minimum principal stress, you could have this large hydraulic fracture, but as long as you are in between these two bounds, for sure, you will not have a large hydraulic fracture, and it's just going to be a short tensile fracture. And the wellbore is going to be still stable. You're not going to have any lost circulation in that case because that's a very tiny frac. And why is that? Why is it's relatively small? It is because the change of stress around the wellbore, if you remember from the equations from Kirsch, does not go very far away from the wellbore. The effect of the changes of stress around the wellbore is actually quite limited, and again, as long as your pressure in the wellbore does not overcome the minimum principal stress, you're just going to have small tensile fracture. And this kind of a small tensile fracture, for example, is the one that we observe in some of these wellbore images where you can see the fractures over here. Here I'm looking at the log here in the middle, or the one in the right. The wellbore was imaged, was stable, was not having low circulation at that time, but the fracture is not too long, and that's okay. You can have that, and that's not an issue. It's going to be stable. All right. So I wanted to clarify that because depending on in which situation you are, your upper bound of the maximum pressure of the wellbore could be either the minimum principal stress in this case, or in this case could be, well, in this case is going to be, well, it's, if PW is larger than PV, in this case could be PV, and in this case could be directly the minimum principal stress. As long as you don't go above the minimum principal stress, that's fine. So here you don't need to exactly stop at PV, you can go a little bit further. But in this one, no, because if you go further, you might have a lost circulation. And sometimes you could even play on the safer side and always set your maximum pressure as a minimum principal stress. The problem of that is that sometimes you may narrow too much unnecessarily what is your mud window. All right, so with this we finish the part of vertical wellbores and the basic mechanics of wellbores and what kind of failures you're going to have around a wellbore, a vertical wellbore. All the questions that we have seen with some slight modifications are going to work also for deviated wellbores, and particularly the equations are almost exactly the same for horizontal wellbores whenever the vertical stress is a principal stress. But let's talk now about deviated wellbores and how we learn. Particularly, first we'll talk about horizontal wellbores, and then we'll talk about truly deviated wellbores, in which they may not be horizontal. All right? We'll start this with an example, just to see and to realize that this is exactly the same thing as what we have been seeing before. All right, let's consider that we have a drilling pad somewhere over here, and we're going to drill horizontal wellbores. Let me add here a coordinate system. I'm going to also assume that at some location over here where we want to drill and where we want to extend our horizontal wellbores, we're going to have a state of stress which looks like this. And it's going to be normal and this is going to be the orientation of stresses, where SV is larger than SH max, and this one is larger than SH min. All right. Question number 1. In which direction would you drill a wellbore for multi-stage hydraulic fracturing? East direction, east or west, any direction is going to be fine. So let's drill the vertical part, and then we'll get to, let's say, the payson somewhere over here. It deviates in this direction. Okay. I agree with that. Let's take a look first at the vertical section. So the vertical section, somewhere around here, position number 1, if I look at wellbore stability at this location, I should look at the wellbore which is vertical, and I'm interested in the plane perpendicular to the wellbore. So plane number 1. For that case, in that analysis of wellbore stability, basically I'm going to be looking at the top face of this cube, and in that top face of that cube I'm going to have a wellbore, and the stresses acting on that plane are going to be SH min and SH max perpendicular to that. Okay, which one is larger? It's obvious, SH max, right? Where would you expect to have breakouts in this particular vertical wellbore in this particular location? You can tell me exactly where. You can tell me, and now tell me east, west, or north, south. If you had breakouts, those would happen.
East, west.
East, west, very well. Somewhere over here. And if you were to happen, I don't know what's happening today with it. Okay, that's better. And if you were to have drilling-induced tensile fractures, they would be north-south, right? But also, if we now look at them not as a line, but as a plane, this would be over here, right? But there will also be a plane which is perpendicular to SH mean. Right? Can you see that? Probably this one, it's getting a little bit difficult to see, but look at the top one. It's a plane perpendicular to SH mean. All right. So vertical wellbore, we know how that works. Let's go now, before I get to position number, this is going to be position number 3. Let me go to another wellbore. Let's just say that in this case, I drill another wellbore, and let me make it deviate a little bit further up. This deviates and then gets into direction north-south. And let's say that this is position number 2. If I want to analyze what is the stability of this lateral well in position number 2, what I have to look at is at a plane perpendicular to that wellbore. And that plane would be this plane, this face, number 2, that has on the plane of that stress, I have acting SV vertically and SH mean on the east-west direction. So this is number 1. Number 2, that's going to be the cross-section of that wellbore. And we said that we're going to have SV and SH mean. Notice that this is the case for this particular state of stress, for normal faulting. If you change this, it's not going to be the same. But if this is normal faulting, we know that the vertical stress is going to be higher than the minimum principal stress. All right. Question, again, where would breakouts occur if we get to shear failure? On the sides or top and bottom? On the sides, very well. Because that's where the maximum compression would accumulate. And if I had tensile-induced drilling fractures, they will occur here, top and bottom, and they would be, if we look in 3 dimensions, they will be planes that again are perpendicular to SH mean. So those planes are meant to, I'm meaning to draw those perpendicular to SH mean coming out from the pitch. And this sort of agrees with what we have already said, that a tensile fracture or a hydraulic fracture should be perpendicular to the minimum principal stress. And if I extend this a little bit further, if I had a problem here of lost circulation, I have a tensile-induced fracture, and then the wellbore pressure goes over the breakdown pressure, and it goes over the minimum principal stress, we would expect this fracture to be something like this, coming out of the page perpendicular to SH mean. Right? And if we had the same thing over here, if we have a small drilling induced tensile fracture somewhere over here, and it continues growing, it's just going to grow always perpendicular to SH mean. If we had, for example, now if I extend this to a hydraulic fracture for completion, if I have two stages and I create hydraulic fractures from those, at some point those are going to link up and they're going to make a large hydraulic fracture, something like this. And this is not convenient in terms of surface area, because you have multiple stages, but at the end you just have one hydraulic fracture, which is not very useful. I mean, you're not taking advantage of the horizontal wellbore. That's why we go into this direction. Okay, so, but drill-induced tensile fractures, you know where they happen in this case, and you know how they will propagate in case of a low circulation event or in case of you're actually doing a hydraulic fracture. Let's go to the third case, which is going to be a little bit more complicated. In the third case, which will be a wellbore, which is really in this direction, we're going to have our wellbore over here. The plane of stresses that we're interested in is this one, number 3, and where we have SV and now SH max in the plane perpendicular to that wellbore. So we have here SV and we have SH max. Again, because this is normal faulting, this is my condition, SV is larger than SH max. And where will breakouts happen in this particular horizontal wellbore? Again, on the sides, on direction north-south, because SV is larger than SH max. And the drill-induced tensile fracture would tend to occur over there. All right, here is where it gets a little bit more complicated, and if you understand this, everything else is going to be a lot easier. Because we are very close to the wellbore can't change the local state of stress around the wellbore. That's because of the presence of the wellbore altering what the state of stress is. And because of that, very close to the wellbore, if you have this tensile fracture over here, that means that in some cases, not in every case, but in some cases, now your drilling-induced tensile fracture may form as a plane which is now looks perpendicular to SH max, and you may say, well, this plane is now perpendicular to the minimum principal stress. And actually it is. It's not perpendicular to the far field minimum principal stress, but it's perpendicular to the local minimum principal stress. Because near the wellbore now, the minimum principal stress is not in direction east-west anymore. Now it's in direction north-south, but just very close to the wellbore. And if now I get this over here, and I have these hydraulic fractures that start propagating in this direction, this is what we see in the wellbore. What's going to happen when they continue growing? So if you remember, we said, well, hydraulic fracture should be perpendicular to the minimum principal stress. Well, the minimum principal stress is in this direction, at least in the far field. So it's going to start then, because of what we have seen over here, it's going to start like a plane in this direction, but as you get further away from the wellbore and the effect of the wellbore is not there anymore, it's going to tend to turn into, this is a difficult drawing, Let me see if I can get it on very beginning. Something like this, where now, okay, let me add a little bit more of inclination to this. I hope you can see what I'm doing it here, but I'm going to explain now with here on the screen. This starts like a plane, which goes in this direction, but as it goes further away, it turns and rotates and gets perpendicular to the minimum principal stress, far away from the wellbore, where the effects of the wellbore are not felt anymore. Now the question is, in terms of drilling, this might not be too bad because you have a constriction here, and therefore the pressure in order to propagate this fracture is going to be higher than without that constriction. But in terms of completion, would you like to have a hydraulic fracture that looks more or less like this? What would happen if you have proppant that has to go through that sort of bottleneck? Very likely it's going to screen out, and all your proppant is just not going to go into the fracture. That's going to be a very narrow passage, and the pressures that you're going to need in order to fracture that also are going to be very high, which is not good. All right. And this is just a very simplified geometry, but it can be a lot more complex than this, actually, with many fractures that segment into various small fractures rather than just one nicely turning. What do you do in order to avoid this? Stresses near the wellbore. Some people also call this the stress cage, meaning that near the wellbore, your stresses can be so high or different that are not the ones that you will see in the far field or in freedom. You do a perforation, right? And what would be the objective of the perforation? Let's do a simple perforation here, like something like this. If you do a perforation, notice that now this is going to be, a perforation is just going to be a small wellbore. And with the small wellbore, and looking, for example, at this one, I'm going to get perpendicular to the perforation a case like that one, where if I have a concentration of stresses around the perforation, still it's going to be good in terms of having those fractures perpendicular to SH mean. And if I look at that one, that's going to be the second one, which is also advantageous for propagating a hydraulic fracture out of those local concentrations of tensile stress. So when you have perforations, you get further away from the wellbore, you get into another direction, which is not the less optimal direction, and your fracture in this case very likely will grow a lot nicer as just one plane perpendicular to SH mean. Sometimes in reality, instead of doing this type of perforations we're going to see later on, you do those at an angle advancing around the wellbore, so that you do not purposely choose what is the optimal direction, but you let the perforations find which one is the optimal. And in that case, you may also have a hydraulic fracture that is going to propagate as just one large plane without its bottlenecks. But again, that's going to be the effect of the near wellbore stresses. Okay, we'll come back to completion later on, but for now, let's continue with drilling. And if you want to calculate drilling stability now for horizontal wellbores, the only thing you have to do is you have to use the same equations, but instead of SH max, for example, in this case, you will use SV. Instead of SV and SH max, you will change this for SH max and SH min. Let me show specifically what I mean with this. Okay, so for example, here in this equation of PV, breakdown pressure, this one is valid for a horizontal wellbore. But if we wanted to analyze, for example, this horizontal wellbore over here, instead of sigma H max, I would use sigma V. And the equation is still the same. If I want to calculate breakdown pressure for this horizontal wellbore, instead of sigma H max and sigma H min, I'm going to use sigma V and sigma H max. But the equation is still the same. And the same for the shear failure and the breakout angle equation. You just have to replace these stresses by the stresses that are appropriate for each case. Okay, so you know that's it about horizontal wellbores. As long as, again, the vertical stress is a principal stress, horizontal stresses are going to be also principal stresses, and as long as your wellbore is aligned with one of those principal stresses, for example, in this case, one SH min, in this case SH max, and in this case SV, the only thing you have to do is to replace the appropriate stress into the equations that we already saw. And for the homework and for the exam, that's all what you have to do. We're not going to get into more complicated equations about how to do this for a deviated wellbore which direction or orientation does not coincide with any of the principal stresses. We're not going to do those calculations, but we're going to see the procedure of how you will have to do that, because it's not too difficult. It's just a lot of math involved in it, and matrix multiplication, and it's not too complex. But I like that you learn how to read some of the plots that are a result of that analysis. All right? So the first thing that we're going to have to do in order to do that is to understand and to be able to plot the direction of any deviated wellbore. And we're going to come back to the stereo net. Remember, the stereo net was a plot in which we have a half sphere and in that half sphere we project, as we did, for example, with faults, the perpendicular direction to the fault, and where that perpendicular direction hits the bottom of the sphere, that would be where we plot our fault. Okay, with the wellbore, it's going to be very similar, but since the wellbore is already aligned, we don't need to do this perpendicular thing. So the only thing we need to do is just to plot the orientation of the wellbore. For example, let's say that, let me finish this plot first, and then we'll do this. Okay, so this is the bottom of that. Again, this is a half sphere. This is the center. Let me zoom in there. This is in 3 dimensions. And let's say that we have a wellbore that goes into this direction, that hits the lower hemisphere somewhere over here, and when you project this on the top, on the horizontal plane, it looks something like this. The only thing we're going to have to do here is to define 2 angles. The first one is going to be the angle between the north and the projection of the wellbore on the horizontal plane. And we'll call this delta, or the azimuth of the wellbore. So again, what we're doing here, we have a direction that goes into 3-dimensional space, the projection of that on the horizontal plane, or if you were looking at that from the top, that line, the angle, is going to be on the horizontal plane, the azimuth, the angle between the north and that line. And the other angle that we're going to use is just the angle between the vertical direction and the direction of the wellbore, and this is going to be phi, the deviation. So when a wellbore is vertical, deviation is 0. When a wellbore is horizontal, deviation is 90 degrees. And by doing this, we can track what is the orientation of a wellbore at any moment during the deviation survey. For example, if I have a wellbore that, let's say that starts a little bit deviated and then goes horizontal, where this is north, east, depth, and it's kind of difficult to see this in 3 dimensions, but let's say that this is the vertical axis. So it starts deviated and then goes vertical. I can divide this trajectory into segments, and that's what you do in a deviation survey. And each of those segments is going to tell me what is the orientation of the wellbore at that particular location. For example, now when we go to this particular case, and remember this is the 3-dimensional interpretation, but usually we don't do all of this in 3D, we just take a look at this in 2 dimensions. With this thing that looks like a target. So deviation 0 degrees is going to be at the center. Let's say this is 30, this is 60, this is 90 degrees of deviation. So for this particular wellbore, you could start, if it starts deviated and it's going, let's say, towards the southwest, it may start somewhere over here. And as it goes, let's say this is this location. As it gets straighter, it might go over here. When you get to the bottom, it goes over there. So the location around this stereo net is going to tell you the orientation of the wellbore. And doing this, you can plot the entire deviation survey of a wellbore. And this is going to look something like what I'm going to show now. It's going to look something like this, where this is the deviation survey of an actual wellbore. If you come back to homework number 1, I think I asked you in homework number 1 to do this plot. So now if you want to do it, you can come back to that file that we used before, use the deviation survey, and make that plot. All right. Can you interpret this plot? I hope you do. For extra points, can you tell me in which direction the wellbore starts? Deviation and azimuth. Anyone? What is not? Oh, the circle is not clear. Let's see if I. Let's see if I zoom in a little bit more. Can you see now? No? Oh, okay, okay. I don't think I'm going to be able to improve this. Basically, the center is here, okay? This is the center. And what you have on the right is in color codes the depth. So yellow, it's the deepest, and blue is the shallowest. So for this particular case, the wellbore starts somewhere over here, starts deviated at about 32 degrees or so, going in direction of, that would be, let's say, 165 degrees from the north. It goes into that location. It goes in direction south, southeast, starting at 30 degrees. Then it goes into that direction, and then finally it gets vertical. All right, why is this useful? Because we can track what is the deviation, and according to the deviation, we're going to get to know whether it is close to failure or not with these plots that we're going to see how to make them probably next class. But let me tell you in the 5 minutes that we have what we have to do in order to calculate stresses around a vertical wellbore. Okay, so the first thing that you have to do if you want to calculate wellbore stability of a deviated wellbore in which now the wellbore does not coincide with any of the principal stresses is you have to calculate, as we did before, you need to calculate stresses in a plane perpendicular to the wellbore, which in this case would be like this plane over here, that circle. And if you want to calculate stresses on that plane, you're going to have to make a change of coordinate system. Your new coordinate system now is going to be the coordinate system of the wellbore. And that's going to depend on the direction of the wellbore. And in this particular convention, we take the first element of the coordinate system as a point going to the center to the bottom of the wellbore, the second one from the center into the horizontal direction, and the third one is directly the direction of the wellbore. That's the coordinate system of the wellbore. You do some algebra, and you can do this change of coordinate system. So your far field state of stress can be now changed to the direction of the wellbore. And further, if you have this in terms of principal stresses, you can do that too, but it's just a change of coordinate system. And after that, you will have a stress tensor, which is going to have all of the elements which are going to be likely different from 0. And with this state of stress, you need to calculate what are the stresses now around the wall of the wellbore. Same thing as we did before. And in order to calculate those stresses around the wall of the wellbore, again, you're going to have radial stress, hoop stress, but now there's going to be a new term, which is going to be a shear stress on the direction which is not on the face of the wellbore, but on the face that goes into the rock. And let's see if I think that I have a plot over here about that. But basically now you have radial stress, hoop stress, an additional term because of shear stresses, a shear stress on the direction theta c, and also the direction in the direction of the wellbore. And basically what you have to do is, with all those stresses, you have to calculate what is the maximum and minimum stress at the wall of the wellbore in this deviated condition, and check whether that goes into tensile strength or tensile failure, or it goes into shear failure. But it is the same thing as we did before, just a little bit more complex and a little bit of a longer path. But at the end, you calculate stresses around the wall of the wellbore, you check whether that it's under tensile failure and under shear failure, and you see if that goes into a tensile, drill-induced tensile fracture, or a breakout as a shear failure. For this case of deviated wellbores, as I was telling before, we have an additional shear stress. And what that shear stress is going to do is going to be a shear stress. If this is the wall of the wellbore, it's not this one, but it is this shear stress. And this shear stress is going to make some of the principal stress to rotate around the wall of the wellbore. And instead of sometimes having a straight tensile fracture in the direction of the wellbore, you're going to have small tensile fractures which are perpendicular to the minimum principal stress. For example, in this case, this one goes in this direction. So you have a tensile fracture. It's not going to be in the direction of the axis, but it's going to be as small fractures distributed along the wellbore. And I don't remember if I have something over here, but no, I don't think I have an image of those fractures. But that's basically what you do, okay? And what I like to talk a little bit about on Friday, and then we'll talk on about the homework, is how you now plot those results for all deviated wellbores, all right? I'll see you guys on Friday.